All right. Okay, so let me get us started. This talk is on incentive design for promoting ride-sharing systems, and it is part of the dissertation work by my former student, Amir Tafreshian, and is supported by the Center for Connected and Automated Transportation, a Region 5 University Transportation Center, as well as the National Science Foundation. Now, as Sarah pointed out, in our group, we look at the next generation of transportation systems, which we envision to be connected and automated, shared, and electrified. But the specific work I'm about to discuss today, it has to do with sharing economy, more specifically, application of sharing economy into mobility markets. And so to get us started, I'm going to give you a very brief overview on the sharing economy and the power it has. So the sharing economy is a fairly old concept that capitalizes on benefits that we can obtain from sharing resources, be it products or services that would otherwise go unused. Now, sharing economy is in general a very powerful business model, including in the mobility market. So in order to back up this claim, I'm sharing with you the results of a study that was a collaboration between the Harvard Business Review and Deloitte in 2014. So in the face of the new technologies that were emerging at the time, they got together and decided to review the valuation trends of the S&P 500 companies during the past 40 years at the time, to devise new business models to see how these companies can create value. And they ended up with 4 business models. First here, we have asset builders. These are companies who develop and market physical products, such as Walmart or Ford, for example. Then we have service providers. These are companies who hire employees who offer a service to customers. You can think of healthcare providers, for example. Then we have technology operators. These are companies who create intellectual property, for example, software, and then sell them. And finally, we have network orchestrators. Network orchestrators create a network of peers. The interactions among whom is what creates value. Now, you can think of Uber or eBay, for example. Here in this figure, we are looking at what is called the average multiplier of the S&P 500 companies whose business model falls within one of these 4 business models. And as you can see, the network orchestrators, they have the highest price to revenue ratio. The price to revenue ratio is generally an important index to look at, first because it is very difficult to manipulate using accounting practices, but also because it shows the potential growth for a company. Companies who have higher values for their average multiplier, these are companies who have higher return on investment and lower marginal costs. So as you can see, the network orchestrator business model is a very high value business model in general. Now, in this figure, we are looking at the percentage of the S&P 500 companies in 2014 that fall under these 4 different business models. And you can see here that the very few of these companies are following the network orchestrator business model. So there is a lot of potential to leverage this business model, but at the same time, it has been very underutilized. And one reason for this is that the average multiplier we are looking at here is for the companies who actually made it to the S&P 500. But it is very difficult to get a network orchestrator business model to work. And the reason for it is that the value is created among a pool of agents who are interacting with one another. And so usually what happens is that there is a critical threshold of participants or agents that are required to have a system up and running efficiently. If we are above that threshold, then what happens is that we could improve level of service, and as a result of that, attract more and more agents. And so we fall into this positive reinforcing loop that makes the system better and better. But the downside is exactly the same thing. If we are below that threshold, then the quality of service is going to be low. And as a result of that, we will start losing participants, and then the system would become worse and worse over time. So when this sharing economy or this network orchestrator business model is applied to the mobility market, it gives rise to likes of peer-to-peer ride-sharing systems. And this is the topic of our talk today. Let me discuss how a peer-to-peer ride-sharing system operates. We have a set of participants or users denoted by N, and the participant could either be a rider or a driver. Now, upon registering their trips in the system, each participant provides the origin of their trip, the destination of their trip, denoted by I and J, respectively, and also the travel time window that is characterized by the earliest departure time of participant N from their origin location and their latest arrival time at their destination location. Now, usually pricing in peer-to-peer ride-sharing systems and in a wide majority of mobility systems in general, it happens based on some characteristics of the trip, for example, the trip's travel time or distance, and also some parameters, for example, evaluation of time, evaluation of every minute a traveler spends in the vehicle, or the valuation of distance. And a peer-to-peer ride-sharing system could have a variety of objectives depending on who is operating the system. So the objective could be maximizing revenue, it could be maximizing social welfare, maximizing ridership, minimizing vehicle miles travel, so on and so forth. Now, before I move on to speaking more about peer-to-peer ride-sharing systems, I want to point out that the peer-to-peer ride-sharing system is different, is operated differently from likes of Uber and Lyft, ride sourcing companies. And the main difference is that the driver himself is driving in order to participate in an activity and not for the mere purpose of transporting passengers. So from a passenger's point of view, this difference is not really noticeable. You request a ride and you receive a ride, but from a systems perspective, this is going to be very important because as research has shown, ride sourcing systems, they can actually add vehicle miles traveled into our transportation systems, whereas peer-to-peer ride-sharing systems could remove vehicle miles traveled and all the externalities that come with it, including congestion, greenhouse gas emissions, so on and so forth. All right, so let me talk a little bit about some of the complexities that we face when we want to operate peer-to-peer supply transportation, including peer-to-peer ride-sharing systems. If you're a person traveling on a network, on a road network using your own personal vehicle, you would be able to travel on any link in this transportation network. However, when you're a rider in a peer-to-peer ride-sharing system, you can only have access to links when a driver is also traveling on that link. So what happens is that you won't have access to all the links present in this road network, but you will have access to realizations of this network. Now, another layer of complexity is that, let's say in a peer-to-peer ride-sharing system, we have a number of driver trips and we come up with these network realizations, all potential possible network realizations. Now, in order to evaluate these network realizations, we have to try to serve all the ride requests that we have in each network realization to see the level of service and ridership we could expect from each of these network realizations. And this problem on itself is an NP-hard problem. For example, let's say we have a single trip request going from this location to this location. In one network realization, we might be able to serve the passenger by following this route, and the two colors indicate two different drivers. So at this point, you can expect the transfer between two different vehicles. Whereas in a different network realizations, you might be able to serve the passenger in a single vehicle, but the route could be, for example, long. So the complexities that arise in modeling peer-to-peer supply transportation are threefold. First, the supply side of the equation is not fixed. Part of it is determined exogenously depending on the drivers who decide to participate in the system. And part of it is determined endogenously depending on how we, as the system operators, decide to route these vehicles and create these network realizations. Now, on top of that, the demand itself is not fixed. It's not known a priori. So the demand will arrive in real time, and you will have to serve it based on the network realizations you have at a time, or you can make a decision on switch to a different network realizations. And the third layer of complexity is that you could have a combinatorial number of network realizations, even for a set fixed number of trips, even when there's no dynamics involved at all. Now, because of these reasons, because of the dynamic supply and demand, what happens is that the matchings that we want to solve, the matching problems that we want to solve between riders and drivers, we usually end up with really low matching rates because the graphs on which we want to form these matches, they end up being very sparse. So then the question is, how can we do it? And this drawback actually goes back to the drawback of the network orchestrator business model that we discussed before. So what are the potential solutions? We could think of many potential solutions. For example, instead of serving demand in real time, we could try to operate a static system where we would require every participant to register their trips ahead of time. And so as a result of that, we'll be working with a larger pool of participants and we could increase our matching rate. But an obvious drawback is that we could lose demand. Not everyone might be excited about having to plan their trips ahead of time. Another potential solution is proactive vehicle dispatching. So we would allow people to request rides in real time, but what we can do is that we can anticipate this demand, and as a result of that, proactively route our vehicles so that they are in the vicinity of locations where we anticipate demand. And so that would reduce the waiting time of passengers, and that would increase the utilization rate of our vehicles. But an obvious caveat here is that basically how well this system would work depends on the quality of the demand forecast we use as input to a model like this. Another potential solution is introducing incentive programs. So these incentive programs could come in different forms. We could try to subsidize rides directly in order to encourage people to participate in the system, or alternatively, we could try to use subsidies or incentives in order to change people's travel behavior. For example, here we have a driver who's traveling through their shortest path because they don't have any incentive to do otherwise. But if we can provide them with some incentive and as a result of that, ask them to take a detour from their shortest path, now they can cover a larger portion of this network. And so there's going to be a higher likelihood of them being matched with a rider. And another solution, the final solution, is using multimodal transportation systems. So in a traditional transportation system, we have multiple layers, each layer corresponding to a single mode of transportation, and they can be operating in parallel. But in a multimodal transportation system, we introduce these links that connect different layers. And as a result of that, we can provide a system whose output is really more than some of the individual outputs of each of these layers. So there's going to be a synergistic impact there. But the specific work I wanted to discuss today was introducing an incentive program. And to be more precise, we are talking about the community-based ride-sharing system, where some participants may be only looking for one-time rides, but some participants may be interested in having a trip in the morning and in the evening. And the motivation behind this work is that one reason why commuters are not really excited about leaving their vehicles back home and participating in ride-sharing systems is that they don't really have a guarantee whether they will be able to get a ride when they need it in the evening. So by providing guaranteed ride back, those type of participants are more likely to participate. So in this new context, now we have a set of trips that happen in the morning. We use n prime to refer to them, a set of trips that happen in the evening, n double prime to refer to them, and a set of trips that happen in the morning and in the evening. And these are the trips who are asking for a guaranteed ride back. Now, if I just want to find the optimal matching in this ride-sharing problem with guaranteed ride back, this is a fairly easy problem. And we can just solve a minimum cost flow problem in order to find the optimal solution to this problem. So in this minimum cost flow problem, we have a number of nodes here that represent driver trips in the morning, a number of nodes here that represent driver trips in the evening. And then we have nodes that represent rider mornings in the evening and rider trips in the morning and rider trips in the evening. We also have two auxiliary nodes here, a start node and a terminal node. Now, we introduce a number of edges between these. So the start node is connected to all the rider nodes in the morning, or if there is all the driver nodes in the morning, and also riders who are only looking for one-time trips, and all the driver trips in the evening are connected to these terminal nodes, plus all the rider nodes that are looking only for a one-time ride in the morning. So in order to create these matching edges between the nodes, we have to consider two types of conditions. One of them is the spatio-temporal feasibility of a match between a rider and a driver, let's say in the morning. So in order for this to happen, we have two simple conditions. If a rider leaves as early as possible in the morning, if a driver leaves as early as possible, depending on their travel time window, and they want to serve a rider, they should be able to pick up a rider, drive the rider to the rider's final destination, and drop off the rider at the rider's final destination within the rider's travel time window. And after doing that, the driver should be able to make it to their own final destination within their own travel time window. So these are the spatio-temporal feasibility constraints. And in addition to that, we have what we call individual rationality constraints. Basically, if you look at this W as the valuation of the ride, sum of the valuation of the ride by the rider and by the driver, it should be positive. If sum of the valuation is not positive, there is no reason for this pair to match in our system. So these two conditions are very strict conditions, and as a result of that, we end up with not many matching edges between riders and drivers. Now, before getting to the solution, how we can use incentives to try to make this graph denser, let me give you a little more information on how we can calculate these valuations. So valuation of a rider R as a result of matching with the driver D in the morning, we could write it down as the product of the rider's valuation of distance times the rider's shortest path travel distance. Similarly, for a driver D, if this driver is matched with rider R in the morning, we can write down the valuation of this driver as a result of this match as the driver's valuation of distance times the driver's detour, plus the driver's valuation of time times the driver's additional time spent in the network as a result of the detour. Now, note that the rider's valuation is always going to be positive if a rider is served, and the driver's valuation is always going to be negative because of the detour that the driver has to take. And then the valuation of a potential match then would be the sum of these two valuations, and that is what we want to be positive in order to have a potential match that is individually rational. Now, as I mentioned before, this graph can be quite sparse for two main reasons. One of them is that usually what happens is that participants have very tight time windows because they want to be at a certain location at a certain time, and they don't really have an incentive to spend more time in the network on their travel. And the second reason is the heterogeneity of valuations. So here what we are doing is that we are expecting riders who potentially have lower valuations of time and distance compared to drivers to compensate drivers who potentially have higher valuations of time and distance for the rides they are receiving. And so as a result of this, both the links that the potential pairs are not going to be spatiotemporally feasible and also individually rational. So the solution we are proposing is introducing incentives. And more specifically, we are talking about two incentive types. The first one we call behavioral incentives or behavioral adjustment incentives, or BA for short. And the idea here is that we want to expand the travel time window of participants. So if we have the original travel time window of a participant N in the morning, then we could subtract from the earliest departure time in the morning some value that corresponds to a time expansion at the origin, and also add some value to the original desired arrival time of the participant in order to expand the time window and have the participant potentially arrive later at their final destination. Now, if you take these two values, gamma minus and gamma plus, and sum them up, you'll get gamma, which is the total time expansion experienced by a participant. And we envision an incentive amount that is proportional to the amount of time expansion, and this based on the participant's valuation of time here. The second type of incentive that we introduce, it's called individual rationality incentives, or IR for short. And this is going to be a direct monetary subsidy allocated to a rider-driver pair. So if we have a rider-driver pair for whom this sum of valuations is negative, we can add a value lambda that to make it positive. And this is going to be our IR incentive. Now, if we want to mathematically model this incentive program, we end up with a very large scale optimization problem. I'm not going to get into the detail, but just give you an idea of what the constraints are. So here we have the valuations of participants after receiving their incentives. Here we have a set of constraints that make sure travel time windows after the BA incentives are introduced are respected. Then we have a constraint that limits time window expansions if we want to put on such a limitation on the amount of expansion we want to propose to people. And finally, we have matching constraints that ensure that each driver is matched at most once and each rider is matched at most once. Now, all of these constraints are only for the morning trips. We are going to have a replication of these constraints for the evening trips. Now, in addition to that, we have an additional constraint for guaranteeing a ride back home for those participants who are asking for it. And also, we want to put a maximum budget of B that we can allocate to any of the two types of incentives. The objective function we are using here is maximizing social welfare, but we are subtracting from it the amount of incentive that we are allocating to people. So the objective is maximizing social welfare minus incentive allocation. Now, this is a larger scale optimization problem, but it turns out that we could decompose this problem in order to simplify the model in general. So first, we have a polynomial-time preprocessing procedure. The idea here is that for each rider-driver pair, we can find the minimum amount of BA incentive that would make their pair spatiotemporally feasible. Now, as a result of this, what we receive is the optimal value for the departure time of the rider and the driver in this pair, and the optimal time expansion that we could propose to them in order to incentivize them. Now, this does not mean that this pair will get matched, and this does not mean that they will receive this amount of incentive. All we are saying here is that if this pair were to be matched, what is the minimum amount of incentive that could make them spatiotemporally feasible? Now, we repeat this for all rider-driver pairs, and after doing that, the problem is simplified now. Now we want to solve an alternative problem where we have a new cost for each edge in the network, and that cost, just like before, it is the total social welfare minus the amount of subsidies we are allocating. And then we have our matching constraints, matching in the morning, matching in the evening, matching for guaranteed rights, and also basically constraint on the total budget we want to allocate. Now, this problem resembles very much the problem we started the talk with. It's a mean cost flow problem that you can solve very efficiently, with the exception that we have a budget constraint here. If we did not have this budget constraint, the constraint set here would have been a totally unimodular constraint set, and we would have been able to obtain the solution to this problem by just solving a linear program. But because of this budget constraints, we cannot, it is not as simple anymore. So instead, what we are doing is that we are solving a Lagrangian relaxation formulation of this problem. So very simply, we are dualizing this budget constraint and solving the Lagrangian relaxation formulation. And now there are very well-known methods for solving the Lagrangian relaxation formulation. So let's assume that we solve this problem and we obtain the solution. And when we obtain the solution, there are two issues. First of all, the solution may not be feasible. We may not satisfy this budget constraint. And also the solution may be arbitrarily far from the solution of the original problem. So in order to improve this solution, we are going to introduce a value epsilon, which is a positive, very, very small positive number. And then we are going to solve two problems. The first problem solves the same formulation we have here, with the exception of assuming that beta here is fixed and its value is slightly less than the optimal value we found in the Lagrangian relaxation formulation. So you can expect the solution we get from this to violate the budget constraint. And similarly, we are going to solve this problem one more time, this time with using beta star plus epsilon. So doing that, we are going to obtain a solution in form of a flow in this graph. We call it SH, and SH is going to satisfy the budget constraint. So having these two flows, one of them violating the budget constraint and the other one satisfying the budget constraint, we want to use a patching method to improve the quality of the solution. So what this patching method does is that it turns SL and SH first into two adjacent extreme solutions, where the difference between the solution is going to be a simple path or a cycle. And after doing that, it is going to modify SH based on gasoline lemma to yield a budget feasible solution. Now, there was a work by Berger et al. That proposed a patching method for the matching problem. We have extended that work to propose a patching method for the mean cost flow problem. And we show that there is a worst case optimality gap of 3 Cmax here, where Cmax is the largest cost in this graph. Okay, so far we have assumed that there is an external budget that we can allocate to pairs of participants in order to incentivize them to participate in the system. Now here we are investigating a budget balance variance of the problem, where there is no external budget, but the funds that we have for incentivizing people could come from taxing those pairs that have a positive adjusted gain to begin with. So let's assume that some of these participants can be matched with a positive adjusted gain naturally. We are going to apply a tax rate of phi here. And this value on the right-hand side will be the total amount of budget that we can allocate to these participants. And then our budget constraint becomes this new inequality that you see here. On the left-hand side, we have the total budget that we can allocate to the pair, to the edge E on the graph as psi E. And across all the edges in the network, we want it to not exceed this amount. Now, we slightly also changed the objective function. Previously, we were maximizing social welfare minus budget allocation. But here, because the budget is provided internally, we are just going to maximize social welfare. Now, as you can see here, as we increase the value of phi, we are going to have more budget to allocate to subsidies, and that would increase this part. But as we increase the value of phi, at the same time, we are decreasing this part. So you see that there is a trade-off as we increase the value of phi. And so the question is, what is going to be the optimal value of phi that would maximize social welfare? Now, it turns out that this budget balance variant of the problem has a closed form solution. You can find the optimal value of phi, and the only thing we have to actually obtain is X max, which is the optimal social welfare of the system if we assume we don't have any budget constraint. And this can be obtained in polynomial time. So in polynomial time, we can find the optimal tax rate that would maximize the social welfare of this budget balance variance of our system. Now, let me show you some results here. First, let's talk a little bit about the performance of the LR solution method. Over here, so these experiments are done using the data from the New York taxi data set. Over here, we are increasing the number of participants in the system from 2,000 to 1,200. And over here, we are looking at the computation time. Now, this red line here, it shows the solution time or computational time of the LR-based algorithm that we propose. And over here, we have the solution time by the MIP solver. And well, the point of it is that the LR solution is much more scalable compared to the MIP solver. Now, in this figure, we are looking at the optimality gap. As we increase the number of participants, naturally, the optimality gap also goes down, which again goes to show that the method is scalable. Now, let's get to some more interesting results. Over here, we are looking at the impact of different subsidy or incentive types. If you recall, we introduced two types of incentives. The BA incentive was the one who try to incentivize people to extend their travel time windows. And the IR incentive was the one where we actually provided a monetary subsidy or incentive to people in order to make sure the total valuation for a pair remains positive. Now here we have the total social welfare in dollars for the case where there is no subsidy at all. And that you can see that for this specific instance of the problem we are looking at, it's a little more than 6,000. Now, if we only introduce the BA incentive, you can see that the social welfare jumps to 18,000. So the BA incentive can be very powerful in increasing social welfare. But if you look at the IR incentive, not so much. IR incentive is not powerful at all. And it is partly because of the way we are designing the system. We are requiring a return on investment of more than one. So we only allocate subsidy to a pair if for each dollar of subsidy that we are allocating to the system, we can have a more than $1 increase in social welfare. And so this requirement is very difficult to satisfy for the IR incentive. For that reason, we don't see a lot of improvement in social welfare as a result of directly giving people money. And finally, here we see two types of incentive at play at the same time. And the result is not that much different from the BA incentive only. It is slightly higher, but not that much different. Now, on the right-hand side figure here, we are looking at the matching rate under different subsidy schemes. So again, the BA incentive is increasing the matching rate from around 17% to around 55%. The IR incentive is actually increasing the matching rate to some extent. We are going from 17 to around 22. So its performance when it comes to matching rate is better than social welfare, but still it is inferior to BA incentive. And again, when we put them together, we get results that are slightly better than BA only, but not that much. And I think this is very interesting result because it shows that if you were to use a budget to say increase social welfare, you would benefit more from using that budget to change people's travel behavior rather than directly injecting the money into the system in form of monetary incentives. Now here we are looking at the results of the budget balance variant. As we mentioned before, there is going to be a maximum matching rate that there's going to be an optimal tax rate that maximizes social welfare, and we could obtain it analytically. And here you see that optimal tax rate is about 18%. Now 18% seems like a large number comparatively when it comes to taxing. But notice that even if we go from 0% in tax to just 1% in tax, we are doubling the social welfare. So even a very small tax rate can be really helpful here. Now, finally, final question I want to answer here is, who are the people who end up receiving incentives? And this figure allows us to have a discussion on that. So in this figure, we are looking at the frequency of the origin and destination zones of trips. So basically, the color here corresponds to the number of trips that originated and were destined at a specific zone. So you can see that in these areas, in the lower Manhattan areas, we can expect to see more activity. Now, in these two figures, we are looking at the relative frequency of subsidized zones. So which zones were the ones that received more subsidies. And here we are looking at the average subsidy per subsidized user of zones. And as you can see, both these figures show that as you move to the outskirts of the city, you are more likely to receive incentives, specifically BA incentives. And these results are also intuitive. So you can imagine, because there's a lot of activity concentrated in the lower Manhattan area, not a lot of trips are originating or destined at the zones that are in the outskirts. And as a result of that, people will receive incentives in order to expand their time windows and make matches actually feasible. If you're interested to learn more about this work, you can use this link to access the draft of this paper that we have uploaded on ResearchGate. Now, I wanted to have a very brief discussion on the pricing. So if you notice, in the beginning, we said that the pricing will depend on some of the trip attributes, such as the duration of the trip or the distance of the trip, but also some information like valuation of time and valuation of distance. Now, we could use historical data to try to come up with a valuation of distance for people residing in a specific city or a specific neighborhood. But what are the implications of estimating these? What are the implications of making errors in estimating these values? And even if we are not making errors, there's going to be individual differences between people who live in the same neighborhood, for example. So what are the implications of using a single value for valuation of time and valuation of distance when we are doing the pricing? So it will lead to direct or indirect loss in revenue or social welfare, whatever your objective is. For example, let's say I'm overestimating the valuation of time of a rider. I will propose to them a fare that they cannot afford. And as a result of that, I will lose ridership and I will lose revenue. At the same time, let's say I'm underestimating the valuation of time of a rider. What happens is that I'm going to give them a fare that they will accept, but I could have given them a higher fare and they would have accepted that too. So that leads to a direct loss in revenue. So then the question becomes, what can we do about it? How can we know the true values of time and distance? And one very obvious answer is that we can just ask people. We can just ask people, solicit this information directly from people. We can ask them when they register their trips, what is your valuation of time and distance? But a very obvious drawback of this approach is that people people may try to game the system by not being truthful in reporting their private valuations. So what can we do about it? Well, there is one thing that we can do about it. We want to make sure that when we are matching people and giving them prices, people will maximize their utilities only if they are being truthful in reporting their private information. If they are reporting higher values or lower values, they will only be worse off. So how can we make that happen? This can happen by means of mechanism design. Now, I'm going to have a slight shifting gear. Previously, we were looking at the dynamic system with guaranteed ride back home. Here, I'm looking at a static bipartite matching, one-time matches in a static fashion. And we only provide incentives to drivers here. Riders will not be receiving incentives. So we talked about introducing now private information. We are going from public information valuations to private information. For a rider, this private information would be a rider's valuation of distance. And for a driver, this private information will be a tuple that is a combination of their valuation of distance and their valuation of time extension. As this information will be used to decide how much incentive they should be receiving. So a mechanism that in general, a mechanism receives information on the trip characteristics of participants, their origins, destinations, travel time windows, and also their private information as they make it available to the system. So this is going to be the input to the mechanism. And the output of the mechanism is going to be a set of allocation or decision rules that decide who will be matched with whom. And also the decision here will be made on the departure and arrival time of participants and the amount of time window extension the drivers can expect. And also a set of payment values that tells us how much a person should pay into the system and how much incentive they will receive. Now, as I alluded to before, a good mechanism has a number of properties. So let's very quickly review these properties. A good mechanism is dominant strategy incentive compatible, basically meaning that, as I mentioned before, we want a person, an individual, to maximize their utility only if they are being truthful in reporting their private information. Then the second property is individual rationality. We want a person to receive a non-negative utility as a result of participating in the system so that we can expect them to voluntarily participate. We want a mechanism to be budget balanced, meaning that the total sum of the payments by the agents plus the additional subsidy, we want it to be positive. We don't want to run a system on budget deficit. We want a mechanism to be computationally efficient. We want to be able to find these payment functions and decision functions in polynomial time. And finally, we want a mechanism to be economically efficient, meaning that we want the mechanism to come up with a decision rule that would maximize social welfare, that would be better than any other decision rule. Now, the subsidy scheme we are proposing here, I'm not going to get into the detail, just give you a very brief overview of how it works. So we are going to start with type-independent allocation. We are going to match people, but in this matching, we are not going to use the private information that they provided, and that is where the term type-independent comes from. And that is partly to make sure that we are maintaining the incentive-compatible property. Then, as a result of this time-independent allocation, we know which participants will be receiving subsidies and which participants could participate without receiving any type of incentive. For those matches without subsidy, we are going to do winner determination and pricing based on a double option that was proposed by Young et al. But for those who will receive subsidies, we are going to do winner determination, pricing, and subsidizing based on random market halving. So I want to get to the details of this, but if you're more interested to learn more, this is a draft of a paper you can refer to. Now, there is a very well-known mechanism called the VCG mechanism. You might have heard of it. And the VCG mechanism is a very powerful mechanism. It can satisfy a lot of these properties except for one. The VCG mechanism is not budget balanced. By the way, there is an impossibility theorem by Myerson that says there is no single mechanism that can satisfy all these properties. So something has to give at some point. So the VCG mechanism cannot satisfy this property. And the mechanism we are proposing can satisfy the first four properties, but not the last one. This mechanism is not economically efficient. So here I want to compare the VCG mechanism with our proposed mechanism to see if it is worth it to give up having economically efficient results in exchange for having a budget balance system. And these are the results. So here I'm showing you different metrics for three different mechanisms. The blue guy here stands for VCG. With the orange color, we are showing the results of the subsidy mechanism, our subsidy mechanism, with a budget of $500. And with the green color, we are showing the results of the subsidy mechanism, our subsidy mechanism, but when the budget is set to $0. So let us start with the most obvious metric here. We have social welfare. And as you can imagine, the VCG social welfare is the highest. VCG is social welfare maximizing. So it is maximizing social welfare. And the two variants of our mechanism, one with a positive budget and one with no budget, they are underperforming as it relates to social welfare. Now, let's also take a look at the matching rate. VCG has a higher social welfare. Obviously, it will end up with a higher matching rate. And again, we have a lower matching rate. Now, I want to show you the payment deficit of VCG though. VCG here runs at a payment deficit of about $2,200. So the total social welfare that the VCG mechanism can provide is about $5,500, but it comes at a very big cost of having a budget deficit of more than $2,000. Now, for our mechanism, our social welfare is smaller. So instead of 5,500, it is 4,750. So there is a difference of 700 and there's a difference of 750 here. But our deficit is equal to the budget we are using. It is only 500. So if you do look at the trade-offs, it seems like we are lower in social welfare, but our budget, we have a handle on how much budget we are spending. Now in this figure, I'm showing you the social welfare ratio. So basically it shows you that our mechanism can capture 85% of the optimal social welfare. And this optimal social welfare is obtained by the VCG mechanism. So the social welfare in percentage is not that bad. We can retrieve a lot of that social welfare, but then again, we have a handle on the budget. So yeah, let me conclude my talk here and leave a few minutes for questions and answers. Thank you for listening to my talk. If you would like to learn more about what we do, this is our lab's website. And if you have any specific questions or would like to be in touch, this is my email address. I'd be happy to take questions.